Hello, everybody. This is Kumar Murthy. I'm director of the Field Institute, and welcome to this seminar. We started the seminar a couple of weeks ago, and we had a couple of weeks of interruption, but now I hope we will take it up on a weekly basis. And today's speaker is Dr. Bragazzi. He's working at York University in Toronto, and you can see the title of his talk there. So, Nicola, maybe you can share your ideas with us.
Okay, thanks a lot. Thanks a lot, everybody, for attending this talk. The title of my talk is Point of Care Diagnostics of SARS Coronavirus 2, Systematic Review and Meta-Analysis of Real-World Data. And in this talk, I will discuss a very timely topic, which is the so-called rapid diagnostic test for SARS coronavirus 2. I will briefly overview the scientific rationale of this talk. As you know, the severe acute respiratory syndrome coronavirus type 2, SARS coronavirus 2, is a coronavirus enveloped single-stranded positive sense RNA virus, which causes a highly contagious infection, which is known as coronavirus disease 19, COVID-19. And the outbreak occurred in late December 2019 in Wuhan, province of Hubei, People's Republic of China, and since then has spread out in neighboring countries, becoming a global pandemic. The virus is highly contagious and as such, timely and accurate and reliable COVID-19 laboratory testing and certified diagnosis is a fundamental step to manage and treat COVID-19 patients and in the effort to curb the outbreak. Both the European Center for Disease Prevention and Control and the World Health Organization are recommending the use of an assay, which is based on real-time polymerase chain reaction using respiratory samples as the gold standard for the COVID-19 diagnosis. However, even if this molecular assay is particularly reliable and useful to diagnose COVID-19, the use of real-time PCR is affected by several practical and organizational limitations. The first is a relatively invasive sampling. The second is a time-consuming procedure to obtain and process the results. Third is the need for highly specialized, trained operators in certified laboratories. As such, the use of RT-PCR is particularly difficult in resources-limited settings, but also in developed countries. The high demand for tests is limited and is straining the healthcare systems and the availability of operational material for the sample collection and for the molecular diagnostics. As such, people are looking for an alternative diagnostic method to avoid overwhelming and straining the public health capacity in terms of laboratories and healthcare facilities, and also to be able to expand the testing capacity to perform a large-scale screening and to ensure a timely therapeutic intervention. So far, some studies have been performed concerning the potential use of rapid testing for the COVID-19. However, the sample sizes are limited and the results are sometimes conflicting. As such, there is a need for an overall updated synthesis of the literature in order to better inform the health policies and guidelines. As such, we have performed a systematic review of the literature and meta-analysis. In particular, we have done a meta-analysis of diagnostic accuracy studies, and we have followed the CADAS-2, which is the quality assessment of diagnostic accuracy studies version 2. Here you can see the reference to the article published in Annals of Internal Medicine. So we have performed the usual steps of the literature search. We have developed a list of keywords based on the published systematic reviews and meta-analysis on the point of care rapid diagnostic testing using synonyms and familiarized with the literature. We have included all the commercially available point of care diagnostic tests. So all the studies investigating all the commercially available point of care rapid diagnostics have been included. Furthermore, we have included studies which compare the new point of care test with real-time PCR, which is the gold standard for the COVID-19 diagnosis. We have included all the studies with the raw number of true positive, true negative, and false positive and false negative results. We have extracted the following data: the setting of the study, the major characteristics of the reference cases, the characteristics of the diagnostic test as a reference, the characteristics of commercially available point of care test, and the total number of true positive, true negative, false positive, and false negative cases. We have performed a descriptive analysis, and we have reported all the characteristics of the included studies. In particular, the accuracy of each study was measured as a sensitivity, specificity, positive likelihood ratio, PLR, and a negative likelihood ratio, NLR, the diagnostics odds ratio, DOR, and the accuracy measured by means of the Cohen's kappa test. As you know, sensitivity is the proportion of positive cases among people with a given disease, in our case COVID-19, and the specificity is the proportion of negative cases among people without COVID-19. The likelihood ratios are the likelihood, the probability that a given test result is expected in a patient with COVID-19 compared to the probability of the same result among people without COVID-19. In other words, PLR, positive likelihood ratio, is the pooled sensitivity divided by 1 minus specificity, whilst NLR, the negative likelihood ratio, is calculated by dividing 1 minus sensitivity by specificity. The diagnostic odds ratio is how much greater the probability of having COVID-19 for the people with a positive test compared to people with a negative test result. The advantage of using DOR is that it is a single measure that combines likelihood ratios by dividing the positive likelihood ratio by the negative likelihood ratio. Finally, the Cohen's-Kappa coefficient is obtained by the Cohen's-Kappa test, and it is a measure that can assess the inter-rater reliability, sometimes also the intra-rater reliability for qualitative items. As in this case, because our measure outcome is categorical, positive or negative. In other words, it's the agreement between the two raters, in this case, the two diagnostic tests, which classify N items into C mutually exclusive categories. If it is less than 0.6, it is weak, while the values greater than 0.9 show an almost perfect agreement. Ranges between 0.6 and 0.8 suggest a moderate agreement. Ranges between 0.8 and 0.9, a strong agreement. Okay, so we have performed a literature review using a string of keywords and extracted all the relevant data. We have done the study protocol, which is registered in the Open Science Framework database, and we have reported and collected the data according to the preferred reporting items for systematic review and meta-analysis PRISMA guidelines. Okay, so now we start to comment the results. We have obtained a pool of 776 items, searching different scholarly databases, in particular PubMed, Medline, Embase, and a preprint server, MedArchive. We have excluded 4 articles which were duplicates, and we have screened 772 articles by title and abstract. After looking at the title, we removed 715 studies, and we screened 57 studies by abstract. After looking at the abstract, we removed 47 investigations, and we assessed the full text of 10 items. Since 6 studies did not report data on commercially available point-of-care rapid diagnostic test, these 6 articles were excluded, and only 4 studies were included in the present systematic review and meta-analysis. 4 articles, providing a total of 9 estimates of accuracy of rapid diagnostic test for COVID-19 versus the gold standard real-time PCR. In this table, you can see the main characteristics of all studies included. We have the study by Lassonnière et al., Cassaniti, Virgilio Paradiso, and Perez Garcia. The first included 30 cases of COVID-19 patients. The second study, 30 negative controls, 30 COVID-19 cases tested with Viva Diagnostics in the real-time PCR, and 50 subjects with suspected COVID-19 tested with point of care in a real-time PCR. The study by Virgilio Paradiso included the largest sample size, 191 cases with suspected COVID-19 cases, sequentially tested with point of care in a real-time PCR using Viva Diagnostics. Perez and Garcia, 45 healthy controls versus 55 SARS coronavirus 2 cases using all test biotech, while the first study last year using several commercial tests, Dynamic, CTK Biotech, Autobiodiagnostics, Acton Laboratories, and Arco Biotech. Based on these results, we decided to perform a meta-analysis. We could not perform a network meta-analysis since the number of commercial tests was very limited, and we could not compare a commercial test against the other. If eventually in an update of the meta-analysis, more data will be available on the commercial test and more commercial tests will be used, we could do a network meta-analysis comparing the different commercially available point of care tests. Okay, so on this table, you can see the sample sizes, the true positive, the false positive, the false negative, the true negative, the sensitivity, the specificity, the positive predictive value, the positive negative value, the accuracy, and the coins kappa. As you can see, the values are quite different from a test to another. For example, if you look at the sensitivity, this value range from 18.4 to 93.3. So the range is quite wide. The specificity is more consistent among the studies and varies between 80% to 100%. The positive predictive values is highly inconsistent and varies between 57 to 100%. The predictive negative values ranges from 26 to 94%. So it is again highly inconsistent. The overall accuracy of the test goes from 36 to 96.8%. And the coins kappa, once again, is highly inconsistent, ranging between 0.05 to 0.935. So the coins kappa varies from a very poor to almost perfect agreement. So the first thing that we can see looking at the table is high variability and heterogeneity of the results. Here we have the first plot of the sensitivity and the specificity. And you can see also here that the heterogeneity measured by the I-squared statistics is very high, is 86% for specificity and 81% and 91% for sensitivity. So the overall specificity is 99.1, ranges from 88% to 99%, using a random effect model. We used a random effect model because the fixed effect model could not be used due to the high amount of heterogeneity, and the sensitivity is 70%, ranging from 47% to 86%. And also in this case, we used a random effect model due to the high amount of heterogeneity. Here we assessed the presence of publication bias using a contour-enhanced funnel plot. And here you have to look at the asymmetry of the funnel plot. It is very asymmetric both for sensitivity and less asymmetric for specificity. So we can conclude that there is an evidence of publication bias, which can be found by visually inspecting the contour-enhanced funnel plot, but also by performing the Edgar's linear regression test, which was statistically significant in both cases, so indicating a presence of publication bias. And here we have the DOR, the diagnostic odds ratio. The overall diagnostic odds ratio is 53.12 odds ratio, ranging from 11 to 242. So we can see that the diagnostic odds ratio is highly variable, and generally is significant, except for one case, which is the study by Castellini using Viva Diagnostics. And here we have the summary of the ROC curve. The ROC is the receiver operating curve. We used a bivariate model, false positive rate against sensitivity, to compute the overall summary receive operating curve, and we obtain an area under the curve. The area under the curve is 0.934, which overall is quite good. And here in this table, we have the summary of all the diagnostic accuracy properties in terms of sensitivity, specificity, the likelihood ratio, the positive likelihood ratio, the negative likelihood ratio, the diagnostic odds ratio, and the Cohen's kappa. So these were the results of our systematic review and meta-analysis. To summarize, we have performed a systematic review of the literature of all studies using commercially available point-of-care rapid diagnostic test for assessing the diagnosis of COVID-19 against the gold standard real-time PCR. We have found 4 studies with a total of 9 estimates of diagnostic accuracy, and we have found an overall sensitivity of 70%, ranging from 47 to 86%, an overall specificity of 99%, ranging from 1880 to 99%, a positive likelihood ratio of 12, ranging from 4 to 34, a negative likelihood ratio of 0.4, ranging from 0.2 to 0.8, a diagnostic ratio of 53%, ranging from 11 to 242, and a Cohen's kappa of 0.6, ranging from 0.4 to 0.8, indicating a not good agreement between the two diagnostic tests. Means the commercially available point of care and gold standard real-time PCR. So the first conclusion is that specificity of the tests that have been assessed in the literature is relatively consistent among studies, which is good, but the sensitivity is affected by a significant amount of heterogeneity and with ranges quite wide between 18% and 93%. So how we can explain this result based on the current understanding of the COVID-19 immunopathology? We can speculate that the median time of antibodies against the virus generally appear between 3 and 6 days after the onset of symptoms for both immunoglobulin M, IgM, and immunoglobulin A, IgA, whilst it may be delayed up to 18 days for immunoglobulin G, IgG. So we can hypothesize that a point of care test, if carried out too early, may have failed to properly characterize the correct immunological status of patients because of this gap in the diagnostic open window. Furthermore, we have to acknowledge some limitations of studies. For example, the studies, part 1, which used a sample of 191 patients, but generally the numbers are quite low, and also the sample power of the studies included is quite low and not satisfactory. Particularly one study in which the performance of one of the commercially available tests was quite poor. So what we can conclude from this systematic review and meta-analysis, that so far there is no evidence that commercially available tests overperform or at least perform equally to the gold standard, which is the real-time PCR. So for so far, the use of this test is currently available for clinical purposes, while of course they can be used for research purposes, but in the clinical setting, the point of care test cannot substitute or replace other more reliable molecular tests, such as assays based on the real-time PCR. So we acknowledge that the use of rapid diagnostic tests would be a good strategy to diagnose COVID-19, also to avoid straining and overwhelming the public health capacity, but so far they cannot be recommended in the clinical setting, and also given the limitations of the studies included, the small number of studies, only 4 studies with 9 estimates, also the small sample sizes, on the 3 studies including the very small sample sizes, part of one study, and also the high statistically significant amount of heterogeneity among the studies, we can recommend that further research in this field is warranted, given the importance of rapid point-of-care diagnostic tests, both in developing and developed countries. And as such, this is the conclusion of our systematic review and meta-analysis. And I want to thank you very much for your attention and for attending this talk.
Thank you, Nicola. I don't know if we have any mechanism for applauding, but you can imagine that we're all applauding. Yes. Now let me see who would like to, we should, if we have any questions, we can start a question method. Maybe Brian, you can moderate. But maybe I will start, Nicola, by asking you, it wasn't clear to me at the outset, the dates of the papers that you selected. What were the dates? Meaning, when did you do the selection of articles?
When this study was done in the last week, so it is updated until I think 5-6 days ago.
I see.
And all the studies were included. There was no time filter, and the systematic review is updated until 1 week ago.
I see. Okay, very good. Somebody should now, I'm sure there'll be questions people would like to ask.
I have a question, Kumar.
Who's speaking?
Masood.
Hi, Masood. Yes, go ahead.
Yeah. So I would like to make two remarks. First of all, when we are dealing, we have to be sure the accuracy of the tests. So it depends on many factors, and therefore the specificity and the sensitivity is no more 100%. So there are a lot of things which affected to that. On the other hand, maybe there is to have some information, we have to have the rapidly testing in order to make a situation. Nicholas, is there any other equipment to use to make a rapid test?
Yeah, I acknowledge that the accuracy is, of course, affected by high range of parameters and, of course, variables. And you mean that there are rapid tests for other infectious diseases?
Yes.
Yes. Yes, of course there are. For example, against malaria, tuberculosis, also for influenza, and the rapid test for malaria, of course, it is a disease that has been studied a lot in the last decades, and so the accuracy of a rapid test is higher for these diseases. And so the aim of the World Health Organization would be to have a rapid test also for viruses, which are quite reliable and accurate, as the rapid test available for malaria or other disorders. But at the moment, the accuracy of a rapid test also for influenza is not so much high.
So the other question will be the following. Assume somebody infected,
yes,
and later recovered. This is your approach can be traced that this control. So then, because as far as I know, the real-time PCR cannot detect this effect. Is there anything to make it that infected, recovered, but the real-time PCR only dealing with this, with the fact which we have. So this is real-time PCR doesn't account this effect.
Yes, the real-time PCR, of course, can trace this situation. Also, the idea of the World Health Organization was to use the rapid test, the real-time PCR, and the rapid test as an immunological passport. For example, when lifting the quarantine measures and when loosening the stringent public health measures implemented so far, the rapid test could be used to quickly screen the immunological status of the subjects and to have a snapshot of the immunological status, like an immunological passport, and to allow a return to the workplace or to other activities.
Okay.
Okay. Any other questions?
Kuma, it's John Hong.
Yeah, sure, John Hong, go ahead.
Yeah, so I have one comment and I have a question. So one of the comments is I want to mention this to the entire audience, that one of the reasons that we encourage Nicola to talk is just want to show there is a capacity within the task force that we have this outstanding fellow, Nicola, who has an MD degree and has a PhD in biophysics and has another advanced degree in public health. So he is one of the best rated top 5 of bioinformatics under the age of 40. So we have such an outstanding fellow that who can conduct real-time systematic literature review of any topic that you feel is important for your modeling work. So we have been taking advantage of this. And I just introduced you this capacity that if there's anything you feel is important for one particular modeling expert, and Nicola can probably help. I know he has multiple projects at hand, but if anything significant, he is available. Secondly, I have a question for you, Nicola. So what does this mean? So in terms of modeling, so we have been using some of the data publicly available, assume some of the results are down through this testing, and you are telling us a really huge variety of testing, the performance of this testing. So what should we do in terms of modeling? So should we do lots of sensitivity analysis of modeling?
Thanks a lot, and thanks a lot for the question. Yes, in terms of modeling, you can use the overall estimates of the sensitivity, specificity, and accuracy of the rapid test to evaluate if the rapid diagnostic test is feasible to be used in different scenarios, like, I don't know, during the outbreak to try to contain the pandemics, or also after the outbreak when people are thinking of reopening activities and coming back to the workplace, and they're using the test as a kind of immunological passport. So, for example, in the idea could be this one, because you know, the availability and capacity of the real-time PCR may be limited. So, which is the best strategy to combine a real-time PCR and a rapid diagnostic test? Which would be the strategy for optimizing the number of people to be properly traced? For example, using a real-time PCR, sequentially testing the point of care and the real-time PCR, point of care alone. So this could be different scenarios that could be simulated.
Okay, may I suggest,
I have the one question, Kumar.
Yeah, I was just going to suggest before people ask
Yeah.
any more questions, if you could just send me on chat your name, then I can order the questions so that everybody has a chance to ask the question. But now go ahead, Masood.
So the other important things which we had in Europe in 2009 in Switzerland, so they due to influenza, it was the following. So all the possible PCR and others, so they are really on one hand very expensive, on the other hand require some infrastructure. If you are quite far from the megapolis, you don't have too much possibility to deal with that. Therefore, I would like to emphasize that the real-time PCR, it's good, but it requires the definite infrastructure, and therefore such a rapid testing, it will be quite late. What do you think about it?
Yes, I agree. I totally agree with you. Yes, the problem of the real-time PCR is not the accuracy, which is quite good, is quite a reliable test. But the problem is that it requires laboratories that should be equipped, adequately equipped. It requires a training of the personnel to perform the test, and require a very high capacity of infrastructures, which is already difficult to have in developed countries, and even more in the resources limited settings. So that's why the rapid tests would be very important in not only in the diagnosis, but all in the entire process of managing an outbreak.
Thank you.
Okay, just before we take the next question, I just want to point out that if you have an interesting topic, you're active in this area, and you would like to share your ideas, we are looking for volunteers for speakers. So just let me know either by chat or by email, and we can schedule you. The format of the talks is pretty informal, and to give maximum time for discussion. Especially a lot of us are now thinking about modeling, the modeling that goes into deciding how and when to reopen the economy. So if you're working on that and you have ideas, I'd like to hear about them in the seminar. Okay, so who has the next question? I don't see anything in the chat. Is there any further questions? Everyone's good? Okay, so if there are no further questions, that's fine. We can end the session early. As I said, I repeat that if you want to give a talk, just let me know or let John Hong know, and we can schedule it. It is not meant to be very onerous in terms of preparation of the talk. It's meant to be pretty informal. And then you can, okay, I see a question here from Melissa Snyder-Adler. You want to ask your question?
Yes. Yes. There are a few studies which do this, but
so we state the question, Nicola, and we should state the question first.
Okay. The
question is, are there any studies that look at these tests compared to serum IgG?
Yes, there are a few studies which do this, but were not included of course, in this present systematic review and meta-analysis because they did not make use of a rapid point of care test.
Okay, is there any follow-up? Melissa, are you okay with the answer?
Yes, I guess I just was trying to look at overall accuracy of these tests when we're comparing it to a slightly different type of test, like PCR, then are you really looking at the same thing? Is it really apples to apples, right? Whereas if you're looking at some of the rapid tests compared to what could be tested for the same thing. I'm thinking more along lines of as opposed to diagnosis, but more immunological passport, as you were talking about, returning people to work, et cetera. So like how accurate are they when we're actually testing what they're looking at specifically? That's, I guess, what my question was. If that makes sense.
Yeah. Yes. In this meta-analysis, we included the studies which measure the immunological status, but using commercially available tests and not other kind of experimentations, if I understood well the question.
Is there any follow-up? That okay? Okay, I don't hear a follow-up. So any other questions for Nicola? Okay, I don't see any further questions. So then maybe, as I said, let's bring the session to a close. Thank Nicola again, and be in touch with us about if you'd like to share any ideas, your recent work with the group. I see there's some sort of icon for clapping. Let me see, how do I? People know how to do that? But anyway, we're clapping. Nicola, you can't hear it, but we're clapping.
I'll do it for you.
Okay, thanks. Okay, thanks everyone.
Yes.
Bye.